students, happy Friday. It is time to finish chapter 16. So far we have introduced the strength of acids and bases, ways that we measure the strengths of acids and bases, namely either concentration or the pH scale. We have introduced how to find pH or concentration if you're working with a weak acid or a weak base. So let's tie everything into a neat little bow before moving into chapter 17, where in chapter 17 we're going to be talking about mixing acids and bases, right? We're going to be talking about neutralization reactions. But before getting into neutralization reactions and mixing acids and bases, there's one last thing we need to talk about, and it has to do with the reversible nature of our acids and bases. Namely, that when you have a weak acid in solution or a weak base in solution, there's going to be a conjugate base or acid present respectively. So let's talk about what a conjugate acid and base mean. All right, so in solution, if we have a weak acids are known to produce weak or conjugate bases. So a conjugate base, as we can see from this example reaction below, is the product of a weak acid dissociating. So our weak acid in this hypothetical case is HSO4-. This is our weak acid. In solution, so if we're assuming this is right in water's taking part, accepting an H+ from this weak acid, we can see as the dissociation occurs, we have a H+ in solution. This represents our H3O+ here. And now we have an SO4 2- left over since the hydrogen has moved onto the water. Now this reaction, as we can see by this arrow here, is reversible. So this SO4 2-, if we were to look at this reaction from the opposite perspective, right, products become reactants, this SO4 2- is able to interact with the water reversibly to create some more HSO4- and some OH-. So we've talked already the reversible nature of the dissociation of these weak acids and weak bases. They're always going to be interacting with water. Because of the water being the solvent, we're always going to have a little bit of H+ and OH-, so the presence of this H+ and the OH- in solution simultaneously should not be surprising, though it is sometimes strange to look at because we think of these two things neutralizing. When they neutralize, we just get more solvent, we get more water. So in solution, we have this weak acid interacting with water, dissociating into a weak base. A weak base that is the result of a weak acid, which in this case we are labeling as the reactant, right? The weak acid is the reactant in this first reaction. A weak base is the corresponding product. This weak base then becomes known as a conjugate base. The existence of this base arises specifically because of the weak acid dissociating. So this weak base now is going to interact with the water and recreate some of this acid, which is going to then be in the first reaction, dissociating to create this weak base. We have this back and forth, right? Again, this is the reversible nature of this weak acid dissociation. So the conjugate base of a weak acid is also the base that leads to its conjugate acid. These two pieces, the acid and the base, are intrinsically linked in solution because of the reversible dissociation in water. So when I say conjugate base, what I mean is the weak base that is the result of the weak acid dissociating in water. And similarly, because again, we have this reversible reaction, this reversible nature, a conjugate acid is the result of the weak base in solution. So in this hypothetical example, we have ammonia. This ammonia is going to interact with the water, and our ammonia is going to behave as a base. It is going to accept an H+ from the water, which is exactly what we see on the product side. An H+ has left the water, has moved onto the ammonia, giving us the ammonium ion, this NH4+, and this leaves us with hydroxide left over. Now this ammonium ion is connected to the ammonia because they are only different by one H+. right? If it has the H plus, it is the weak acid corollary. If it's missing that H plus, it becomes the weak base corollary. But this is what we mean by a conjugate system. A weak base is going to lead to a conjugate acid, and a weak acid is going to lead to a conjugate base. It is the resulting base or the resulting acid from the dissociation in water. And so we label these not in isolation, but sort of like how redox reactions, if we think back to redox reactions, the gaining or losing of electrons, we always refer to this type or that type of reaction as a redox reaction because reduction and oxidation always happen together. Here, with our conjugate acids and our conjugate bases, we label these in reversible weak acid, weak base reactions as conjugate acid-base pairs because similarly, they always also occur together. A Bronsted-Lowry acid and base that differs from each other by a single H plus ion, which is what we have already introduced, is a conjugate acid-base pair. So in the following reaction, we have not just water being present, though water is present in solution since each of these species are labeled as being aqueous, right? Each of these following molecules is dissolved in water in this kind of reversible reaction scenario, and we can label the conjugate acids and bases in the following reaction much the same way as what we did with the water, or when the acid and base were only interacting with water. Here now we're kind of mixing acids and bases, but we can partner each of the reactants with one of the products. And the way that we're going to partner these is, here we see the HCOOH. This is formic acid, is only one hydrogen different than this HCOO minus. This causes the HCOOH on the left and the HCOO minus on the right to be a conjugate acid-base pair, where the weak acid I'm just going to label as a WA, and the conjugate base, I'm going to label as a CB. We always, just for convention's sake, list the conjugate label on the product side, but this is only conventional standard, right? If we were to reverse this reaction and write the products as reactants and the reactants as products, we would still keep the conjugate label on the product side, just by conventional standards. The other molecules that are left in the reaction, we have this F minus, this fluoride ion. If this were to gain a hydrogen, it becomes hydrofluoric acid, which is exactly what we see on the product side. So this F minus we're going to label as the weak base of the reaction, and the HF we are going to label as the conjugate acid. So the weak acid and the weak base could hypothetically be pulling or donating the hydrogen into solution, like into the solvent, or they could be donating it directly to each other, right? So this weak base could be pulling the weak or the hydrogen directly off of the weak acid, which is the nature of an acid and a base interacting together. We have the swapping of the H plus from one to the other, which is exactly what leads to the products that we see as a result. So here we're getting a little bit into mixing acids and bases, but the important takeaway is that we are learning to identify the conjugate acid-base pairs here. Which species in solution, reactant and product, pair together because one has either donated a hydrogen or accepted a hydrogen, and then the product is the corresponding conjugate acid base as the result. Okay, so how then do the conjugate acid base pairs actually link together in solution? So, and like what are the relative strengths? Because due to the nature of water being our solvent, there is actually a connection between the strength of our weak acid and its corresponding conjugate base, or the weak base and its corresponding conjugate acid, right? Because water dissociates reversibly in solution, giving us H plus and OH minus. One thing that we talked about as a result of water being our solvent is that our pH scale is kind of capped between 1 and 14. And this is just the nature of the water dissociating into the H plus and the OH minus, and the balance that needs to be kept between the H plus and the OH minus. Similarly, if we have a weak acid and its corresponding conjugate base in water, the amount of H plus and OH minus that can be generated by these reactions must also adhere to the solvent, being water's nature, its dissociation, and it being the conjugate acid-base pair has to play also within the brackets of this pH of 1 to 14. So because of this, what we actually have found in conjugate acid-base pairs is that a stronger acid is going to result in a weaker conjugate base. Right? If we think back to one of the calculations that multiple calculations we've been doing Monday and Wednesday, if we were to increase the concentration of H+, let's say in solution, we have found that the concentration of OH- has to decrease as a result of that. So if we have something that is a very strong acid that is going to be increasing the H+ concentration, in the reversible reaction, the amount of base that is going to be creating OH- is going to decrease. We're going to have less OH-, and because of that, we're going to have a weaker conjugate base. Similarly, if we have a weaker acid, so we don't actually get a lot of H+ generating in solution, because we don't have as much H+, that is the result of a stronger conjugate base where we're actually getting a lot of OH- there being present in solution. So again, we are thinking of this in terms of our seesaw. If we have H+ and OH- just in neutral water, they are of equal amounts, equal concentrations, but as soon as we introduce a strong acid, the OH- concentration is going to have to go down and vice versa. So in the diagram below, what we have labeled is acids up on top, and the stronger acids are listed on the left, weaker acids are listed on the right. So we have this relative scale going from strong acid on the left all the way down to weak acid on the right. The second bracket that is underneath the acids are the bases. Specifically, the bases that are listed exactly correspond to the acid up above. So we can see here we have HF. On the acid side, we can see it's listed kind of closer to the stronger acid side, so it's going to be generating plenty of H+ in solution. The corresponding conjugate base, F-, is listed directly down below. Now we can see that its Kb is pretty small compared to the Ka of the HF, meaning that we're not going to be getting a lot of OH-. Our higher Ka means that we will be getting plenty of H+. And we can see that this is true across the entire diagram, that weaker bases are going to be on the left corresponding to stronger acids, and the stronger bases on the right are going to be corresponding to weaker conjugate acids. Let's see, and on the far ends of the spectrum, we can actually see that water is present. So the strongest of the strong acids is actually hydronium. If this hydronium were to lose one of its hydrogens, the corresponding weak base would be water. And we know that water is perfectly neutral if it is the solvent, right? If only water is around, then we have this nice pH balance of 7. And we define pH using this H3O+, so it makes sense that this is, right, the strongest acid that we would consider. It's what sets the benchmark inside of solvent for what it means to be a strong acid. If we look to the far right-hand side of this diagram, where water is being considered as the weakest acid, its corresponding conjugate base is OH-, and OH- is what we use to set the bar for what it means to be a strong base. So water is both the weakest acid and the weakest base. The conjugate acid and base of water are the strongest acid and the strongest base that you can possibly have in solution. Again, because these are what set the benchmark of a pH of 1 for hydronium and a pH of 14 for hydroxide in solution. Okay, so I just mentioned Kas and Kbs being used as a measure for approximately how strong or weak your weak acids and bases are. So is there a way to link together the Ka and Kb of, let's say, a weak acid and a corresponding conjugate base, right? Wa for weak acid, looking at its Ka, and the Kb of a corresponding conjugate base. So this isn't just any acid and base. This is specifically for a weak acid and its conjugate base pair. And the same example could be applied to a weak base and its corresponding conjugate acid. We can use our Kw as a measure for relative conjugate acid conjugate base strength. So here we have this equation that is set aside. Our Kw is equal to Ka times Kb. And again, this is for specifically a weak acid, weak base, conjugate acid base pair kind of situation. You can't use this just for any Ka or Kb. It has to correspond to the weak acid and its weak base counterpart. The reason why this equation is the way that it is, like how we derive it, is we start with what our Ka is classically defined as. So if our Ka corresponds to some generic kind of weak acid dissociating in solution, the Ka that we can write is going to be equal to the product of the concentration of our products, the H plus and the A minus, all divided by concentration of HA. And our Kb, we're also going to similarly define starting from the conjugate base of the weak acid that we had first added into solution in our kind of first generic hypothetical example. Our A minus interacting with water is going to give us some more of that conjugate acid back, as well as OH minus. And so our Kb here is going to be equal to the concentration of our HA times the concentration of our OH minus, all divided by A minus. All right, so if we were to take Ka and Kb and multiply them together, Ka times Kb, right, so I'm just gonna bracket these off. So we're looking at these now being multiplied together, this x being our big multiplication symbol. We can see that the HA in the numerator on the right is going to cancel with our HA in the denominator on the left. Our A minus that is in the numerator on the left is going to cancel with our A minus that's in the denominator on the right. And what this is going to leave us with is H plus times OH minus. So here's our concentration of H plus times concentration of OH minus, which is exactly equal to our definition of Kw. So here we can see again, so long as we are using a conjugate acid-base pairs Ka and Kb, the multiple of these two equilibrium constants will be equal to the special equilibrium constant for water. So let's say we are looking back to that hypothetical first weak acid that we had in water, the HSO4 minus. It is known to have a Ka that is equal to 1.02 times 10 to the negative 7. We can use this information to find what the Kb is of the weak base. So just to rewrite our generic dissociation that we had seen, our HSO4 minus was interacting with water reversibly to generate some H3O plus and some SO42 minus. So we already know what the Ka is of this reaction in the forward types of direction, right? Our Ka is equal to 1.02 times 10 to the negative 7. So if we want to consider the reverse reaction, not necessarily like the pure reverse reaction, but now we're taking the conjugate base, and the conjugate base is interacting with the solvent also, regenerating our HSO4 minus as well as some OH minus, Ka here is equal to 1.02 times 10 to the negative 7. We want to know what our Kb is equal to. Well, all we have to do is take the equation that we have just learned. We just learned where it was derived from. Our Kw is equal to Ka times Kb to find what the Kb is equal to. Right, so our Kb is going to be equal to our equilibrium constant for water, our Kw, all divided by the Ka that we just learned. So if we take 10 to the negative 14, which is our Kw, right? That's an equilibrium constant that is always going to be constant so long as we are working at the same temperature, which in parentheses, right, as an addendum here, all of the calculations we've been working through so far, we are assuming that we are at or near room temperature. We have not been varying temperature at all. So I want that to be explicitly clear. This Kw will change if we change the temperature of water, but we are not going to be doing that. All right, so we have our Kw. It is equal to 10 to the negative 14. We're going to divide by the Ka that we have just been told, the 1.02 times 10 to the negative 7. And this is going to give us an overall Kb, let's see, that is equal to 9.80 times 10 to the negative 8. All right, so if we want to compare the Ka to the Kb, what this tells us, whichever value is higher, this is the overall, we would say, like, molecule or reaction that is dominant in aqueous solution. So because our Ka is higher, it is larger than our Kb, we would say that HSO4 or HSO4 minus is a stronger weak acid than what SO42 minus is of a weak base. So this SO42 minus is a weaker weak base than what the HSO4 minus is of a weak acid counterpart. So the dominant reaction inside of this aqueous vessel is going to be the dissociation of the HSO4 minus, not by much, right? It's only of a factor of 10 higher, a multiple of 10 higher, but that does mean that we are going to have 10 times the acidity compared to the basicity inside of solution. Okay, so the last topic that we need to address when it comes to looking at the nature of these acids and bases before we start neutralizing them and mixing them together. Every acid really that we've been working with so far, like all the way back to example 1 in this chapter, has been assuming that every acid that we've been working with is monoprotic. But what happens if we are working with diprotic or even polyprotic acids, where a diprotic acid is an acid that has 2 ionizable H atoms, which would be something like H2SO4, or a polyprotic acid, which is just an acid that has multiple ionizable H atoms or H ions, something like what is illustrated below, which is H3PO4. Here we have the Lewis structure illustrated for H3PO4. We can see that each of the hydrogens is directly bound to an oxygen in this molecule, and each one of these hydrogens is going to be potentially ionizable. Each one of these hydrogens could be potentially lost to the aqueous solution. But the question is, which is going to be the most likely? Like, are we going to more than likely just lose 1 hydrogen? Are we going to be losing 2 hydrogens? Are we going to be losing all 3 hydrogens? Like, how strong or how weak is the ionic dissociation of the hydrogen in these acids? Right, so this is going to tie us into measuring the pH of polyprotic acids. And I'm going to be using polyprotic acids to also include diprotic acids, since technically poly just means more than one. So I'm going to lump diprotic into that as well. So one example of a diprotic or polyprotic acid is maleic acid. Now, if you've ever had a Sour Warheads candy, the white powder on the outside of the candy that causes that incredibly delicious sour flavor is maleic acid. It is extracted from fruits. It is naturally found in fruits. It is also what gives us the sour flavor inside of fruits like apples and pears. This is not the sour flavor that comes from citrus fruits. That is citric acid. Maleic acid's a little bit different. Different in flavor, different in sourness, but the maleic acid is what is causing that type of sourness in like Warheads candies, Baby Bottle Pops, basically any of those incredibly sour candies that you can buy on the shelf that were like pulled from shelves for a while because parents were concerned for like their kids' teeth. Maleic acid is polyprotic. There is a larger than 1, right, number of hydrogens that can be ionized. Here's the structure of maleic acid below. There is 1 hydrogen, 2 hydrogens. Structurally, both of these hydrogens are identical, so we could have picked either one of these to be hydrogen 1 and hydrogen 2. But what we've been able to find experimentally is that the first hydrogen, which I have labeled here on the right, this is the first hydrogen lost, has a much higher K, a much higher pK than what the second hydrogen does. We actually see 2 distinct points where we lose our H+. It doesn't happen all at once. We don't lose both of our hydrogens all at once. Losing the first hydrogen is easy. And this we have found to be consistently true, not just in like maleic acid, but across any polyprotic acid. The first hydrogen lost is always the easiest. And the reason is that an acid by nature is going to lose at least 1 hydrogen. But after 1 hydrogen is lost, right, if we've lost this H, it is now an H+ gone in solution, we have a minus charge on top of this molecule. And yes, it's on this oxygen, but this oxygen, as a result of the negative charge, is going to be wanting to disperse that negativity to the rest of the molecule. Because there's already an abundance of electrons in the molecule, this second hydrogen that is labeled here is going to be harder to lose. Because if the molecule loses a second hydrogen, that's even more negativity, pushing it away from this like neutral charge. So for every additional hydrogen that is lost, it becomes harder and harder to lose another hydrogen. So in maleic acid, we have found that there are 2 distinct Ks, 2 distinct equilibrium constants for this reaction. The first is pretty skewed towards product. It's actually a fairly large K value. It's still a fraction, right? We still have partial dissociation. We still have plenty of reactant left over. But compared to the second equilibrium constant, this value is pretty high. And we'll talk about what the pK means in a second. So we're just focusing on the Ka first. The second hydrogen we see here is a much lower number. This corresponds to the idea that I just proposed, that the second hydrogen is harder to lose. Remember that small equilibrium constants mean that we have more reactant than what we have product. So here we, in the second Ka example, are looking at a lot of reactant, not a lot of product. We still have some product, it's just not a lot of product. All right, so what the pKs stand for. Remember back when we introduced pH, this was, the P was a representation of negative log of whatever the thing is that we're measuring. pH means negative log of concentration of H. pKa means the negative log of your Ka. What this is useful for, since so many of our acidic equilibrium constants, like we can see here, are decimals, it just puts the decimal into a number that is more akin to it's on the logarithmic scale. It's easier to read like on the pH scale. So this pKa being equal to 1.92 means that this Ka results in something that is more acidic. The second hydrogen that is lost and its corresponding pKa2 here is labeled as a 6.33. This is something on the pH scale that is more neutral. There's not a lot of additional H plus being lost into solution. In fact, there's such a small amount of H plus being added into solution that it basically behaves like slightly acidic water. It's basically water. We get such a little decomposition, such a little dissociation of H plus into solution from this. Okay, so the last type of example problem we're going to look at then is if you are working with a polyprotic acid, if we have multiple dissociations, how important is it that we include all of these dissociations? How much of an effect does the dissociation of that second hydrogen have compared to the first hydrogen in solution? So let's look at the maleic acid that we've just introduced. If we have a 1 molar solution of maleic acid, it's going to taste incredibly sour. The question is, what is the pH of that solution? And for this example, we are going to take into account both dissociations just to illustrate how important it is that we take either just one dissociation or both dissociations into account. The way that we are going to start this problem is much like how we have started any reversible reaction type of problem. We need some type of balanced chemical equation. A balanced dissociation. So I did illustrate what the chemical structure of maleic looked like. We could write out its entire formula, or we could shorthand and say that this is just some type of HA. Either way totally works, just so long as you remember that HA stands for maleic acid. So the first dissociation, we are not actually just going to label this as an HA, but since this is a diprotic acid, right, there were two ionizable hydrogens, we're going to label this as H2A. That's going to be important since we are going to be looking at first the loss of one hydrogen and then the loss of the second hydrogen. So the loss of our first hydrogen, we're just taking it one step at a time. Since we have two distinct Kas, we're going to have to take this one step at a time. Our first dissociation will give us an HA minus as a conjugate base and H3O plus. Each of the ionic species is aqueous, much like the maleic acid that we first dissolved in water. Since this is a reversible reaction, we're going to have to use an ice table to figure out exactly how much H plus is there in solution after this first dissociation. So we know that the concentration of our H2A is 1 molar. We're sticking with 1 molar just to keep the calculations here pretty easy. Water, again, we never have to worry about in solution. Initially, we are going to assume that there is no dissociation, where we're taking this 1 molar solution, or this 1 mole of maleic acid, putting it into a liter of solution. Now we want to know how much dissociation has occurred. And even though the Kas are not explicitly listed on this slide, we are working with maleic acid. The Kas were listed on the previous slide. So it's going to be pretty easy to be able to calculate what the change of the dissociation is, since we're going to be losing some of our H2A and generating some product. At equilibrium, then, we should have 1 minus X for our concentration of our maleic acid, and X for each of the conjugate base and the H3O+. Okay, so our Ka that we can set up, since this is the first dissociation specifically, this is going to be Ka1, so I'm going to label that as Ka1 so we don't lose track of what all of the equilibrium constants are, like where we are in the problem. The measurement then of our equilibrium constant is going to be equal to the concentration of our Ha minus times the H3O plus, all divided by concentration of H2A. Now here we can substitute in for the values from our equilibrium table, our ICE table, where each of the concentrations for our Ha minus and H3O plus are X. So when we take that together, we're going to get an X squared. Concentration of H2A is going to be 1 minus X. All right, so I myself went through the process of taking all of this, which is now equal to our Ka1 from the previous slide, which is 0.01259. I rearranged all of this into a quadratic and then used the quadratic formula, which here I am going to encourage you to pause the video, work through that math. You can be able to, or then you will be able to check your answer to what I am going to write down here in a brief second. Again, I want to make sure everyone's getting an abundance of practice using this more complicated math. The reason why we have to use the quadratic formula, we can't take a shortcut here, is because our Ka is not at least 1,000 times smaller than our initial conditions. So we are going to have to go through the more complicated route to find whatever our X is going to be equal to, of which our X for this problem is going to be equal to 0.106 molar. All right, so this 0.106 molar is equal to the concentration of our H3O plus. However, the problem is not yet entirely finished, right? This was only the first dissociation. We're not going to calculate a pH yet, because what we want to find is, does now the dissociation of the weak base lead to a significant increase in this concentration of H3O+. All right, so if we want to solve for what the second dissociation is, what we need to do now is start with the amount of Ha minus that we have once we have reached equilibrium after this first step. So in this calculation, we are assuming that all of the H2A is going to reach equilibrium first, generating some Ha minus, and then this Ha minus is going to go on as a, it's the conjugate base. It will be in solution, acting as a potential additional acid, losing some more H into aqueous conditions. So we're going to start now with the concentration that we have just calculated of the HA, this 0.106 molar HA, and this is going to be the amount that is going to start breaking up in the second step. So if you haven't written everything down, please do so. I am going to erase the slide and start the second set of calculations just to demonstrate what the polyprotic acid calculation is going to look like. All right, so everything's been cleared, board's been erased. We are now taking the second hydrogen from the HA minus, right, the maleic acid that has already lost one hydrogen. It is a polyprotic acid and has the chance to lose the second hydrogen. So if it loses the second hydrogen, this is going to leave an A minus in solution and another H3O plus from the remaining solvent. Remember that a solvent is defined as being the molecule that is the most abundant in solution, so we have plenty of pure H2O to go around. This is definitely a reaction that could possibly happen in solution. There's enough H2O floating around that it hasn't all been converted into H3O plus from the previous reaction. So if we have the HA minus interacting with water, generating some of its now conjugate base and some H3O plus, we are starting with an initial amount that is going to immediately pick up from the previous reaction reaching equilibrium. In other words, we're going to start with 0.106 molar HA minus. there's going to be some type of change, and we're going to reach a second equilibrium. All right, so there are a couple of different ways that we can go about solving for this problem, and it all has to do with how we set up our initial conditions for the products. Now, obviously, we don't have any A- present in solution. Nothing here was generated from the previous reaction. However, there was some H3O plus generated in the previous problem. So either we can kind of like take that number that we have and set it aside, let this concentration here for this new type, this new generation of H3O plus be equal to 0, and then we take those two numbers from the two separate calculations and add them together. Or what I find is easier and is more self-consistent, since we pulled this 0.106 molar for the HA- from the equilibrium conditions of the previous step, I'm going to also be consistent and say that we are starting with also 0.106 molar H3O plus from the previous step, right? We generated some H3O plus. It is floating around in solution. I don't think that we should just neglect that. Whatever route you decide to take, because the textbook describes the first method that I just kind of verbally laid out, both will give you the same answer algebraically. I find this method I'm about to lay out easier to stick with conceptually, since we're not making any like mental exceptions. The math ends up working out a little bit easier in the first case, but I think conceptually the second case is easier. Okay, so in the change row, we need to figure out which direction this reaction is going to shift. Is it going to move from reactants to products, or is it going to move from products to reactants? Well, since we don't have any A-, we are going to have to shift from reactant to product in order to generate some of that product. So we're going to be losing HA, or HA-, we're going to be generating some A- and potentially also generating some additional H3O+, right? That's the whole purpose of doing this second calculation for a polyprotic acid, is we want to know how much additional H3O+ is being generated here. So at equilibrium, we will have 0.106 minus X, we will have X, and we will have 0.106 plus X. All right. Our calculation for our to find our X then is going to be Ka2, right? This is our second hydrogen that we are being lost. There is a special second equilibrium constant for this second hydrogen, which is equal to concentration of A- times H3O+, all divided by HA-. All right, so we're going to take the values from our ICE table, insert them into the concentration values at equilibrium for these values here. Our A- is an X, our H3O+ is a 0.106 plus X, and the reactant is a 0.106 minus X. All right, our equilibrium constant from the, like 2 slides ago, or no, still just 1 slide ago, for our maleic acid, the second dissociation was a 8.511 times 10 to the negative 7. All right, so here we have an equilibrium constant that is at least 1,000 times smaller than our new initial conditions, right? This is 1,000,000 times smaller than our initial conditions, which means that we can drop a plus X. We can take a shortcut. And I can guarantee I've gone through the math the long way. It does work out the same. The reason why I'm specifying that is because of the answer that we're about to see. The plus X that we end up removing, or the minus X we end up removing, is any of these changes from initial conditions that are at least 1,000 times larger than our Ka. In other words, we can assume that our Ka is going to be approximately equal to X times 0.106 divided by 0.106. The changes from the initial conditions are going to end up being so small that the changes don't matter in either case. So we can cancel those out. Our X value, our change, is going to be approximately equal to 8.511 times 10 to the negative 7 molar. Which means if we want to calculate what our concentration of H3O+ is, so we can actually get a measure of pH, the change away from the equilibrium conditions after the first dissociation is so small, we didn't actually even have to do any of this math there was no significant change, right? 0.106 plus 8.5 times 10 to the negative 7 is approximately 0.106. We don't see any significant change due to significant figures. So why did we go through the entire second calculation? Well, I wanted to demonstrate explicitly that if you're working with a polyprotic acid, specifically if your Ka2, your Ka3, potentially even your Ka4 are very small values like what we just saw, the Ka2 here was something times 10 to the negative 7, we assume that the dissociation of the additional hydrogen is so negligible, we really only have to pay attention to the first dissociation. Sometimes you will have to pay attention to the second, but what's going to matter, like how you can tell if you need to pay attention to the additional dissociation, is going to specifically depend on what your magnitude of K is. If you see that your first K is something times 10 to the negative 2, and suddenly your second K is nearly 1,000,000 times smaller, feel free to not even do that second calculation, because your first dissociation is going to be the only meaningful dissociation. All right, so let's actually solve this problem then. Your pH is going to be equal to the negative log of the concentration of H3O+. And for your polyprotic acid, despite the fact that maleic acid has the chance to lose 2 hydrogens, only the first dissociation we saw mathematically actually mattered. So the negative log of your concentration, that is 0.106, is going to give you a pH that is 0.975. Even though this is a weak acid, and the second dissociation doesn't really matter, what we can see here is that your pH is still incredibly acidic. So I'd hinted that, like, there were certain candies, right, pulled from the shelves because parents were worried about their kids' teeth. Warheads specifically. I was a kid when those were pulled from the shelves. They went from being everywhere to being nowhere because parents complained. This pH is exactly why parents would complain. A 1 molar solution is not hard to obtain for this maleic acid inside of your mouth when your saliva is the solvent. The maleic acid gets very concentrated, and that change in pH to incredibly acidic conditions can cause a lot of plenty of decay inside of your mouth. It's not to say that you can't enjoy a good warhead every now and then, but everything in moderation. Okay, with that, we have finished chapter 16. Here we have some section review problems for conjugate acid-base pairs. So if you want to get some practice being able to identify some weak acid as it is dissociating into its conjugate base and the H+ ion, or a weak base and its conjugate acid, here are the first set of problems. If you want some more practice looking at the diprotic and polyprotic acid cases, here we have another couple of problems to work through. If you have any questions, do not hesitate to let me know. Let's see, brief announcements now that we are at the end here. Homework. Since next Monday is Easter Monday, and I'm giving everyone like technically a break, there's not going to be a lecture that's required for next Monday. Your homework also is not going to be due until next Wednesday. So if you want to take the weekend to be with your family in whatever way that's going to mean, whether it be Skype or, spending like a special quarantine day or whatever your day is going to look like, I'm giving you guys that Easter weekend. Like, we're all in hard times right now. Take the time that you can with your family and loved ones, whatever that's going to end up looking like. Next week also is going to be exam 4. My plan currently is to post that on Sunday, but you will have all the way until Friday to get that turned in back to me. So even though I'm posting it Sunday, don't feel the obligation to start it on Monday. I just want to, get that posted in as much advance as possible, so that way I am not going to forget. Mainly that's the reason. I don't want to forget. I want that to be available to you. All right. I'm also recording this lecture after Dr. Arn's email had been sent out, which has announced that classes are going to be online for the rest of the semester. I also had said on Blackboard that I'm not exactly sure then what the nature of the ACS exam and final exams are going to be. I can also confirm that we are still talking as a department to figure out exactly what those expectations are going to be. As soon as I figure out what the nature of the ACS exam is going to be and what the final exam is going to be, I will let you guys know as soon as I know, I promise. We're just trying to have a very hard conversation about what types of exceptions we're going to be making for this current class, not just you guys as freshmen, but also the current sophomores, the current juniors, and the current seniors, since this is an unprecedented pandemic event. We're trying to figure out exactly how this is going to affect expectations, not just for us, but in the greater picture. So once I have that information, I will relay it to you guys. I'm not leaving you in the dark on purpose. I just genuinely don't know what it's going to look like yet. With that, I am going to stop with the announcements. That's all I have for the day. Excellent work, everyone. We're going to get through this. We're going to round out the semester. You guys have been doing great work, great jobs. So yeah, have a great Easter weekend. Get as much rest as what you can or